over I0 is the loss of energy. Okay? And this loss of energy is related to the density of the material. For example, if in this short interval, this interval is called dl. In this short interval, if the coefficient of absorption is F, this is related to F of x and y dl integral over L. This is the absorption coefficient multiplied by the length of the trajectory gives the total absorption. Okay? Actually, and this is the main equation, the main physics that you need to handle with. Now we have to go to be a little more precise. Did you understand this equation very well? Is it so? F is the absorption coefficient. The absorption coefficient multiplying by the length gives the total absorption. Summing over the length, over the whole length, this is the length, this is the line L, gives the total absorption. So what is measured here is related to this equation. Now consider that you have moved the sources and the detectors, or you have many detectors placed on a line. We are going to talk about what is called the parallel geometry. And so I am going to give two parameters, that is angle phi. So this is the angle phi. And I am also going to put this distance as r. So the quantity that I am going to measure here, this quantity this is g at angle phi at position r. Or I can also write like this. The value of this absorption coefficient, which is measured by the detector at position R at angle phi, is noted G. If the angle is constant, and if R change from this, okay, I change the values of R. For each position of R, I will have here a function which is exactly this function. So the equation that I have to write is G of R and phi is equal to integral over L of f of x and y dl. This line L, equation of this line L depends to two parameters, R and phi. So this L depends on R and phi. Equation L, R and phi, it is very easy to write the equation of this straight line. The equation of this straight line is x cosinus phi plus y sinus phi equal to r. It is very easy to check this. And so using this equation, r cosinus phi and r x cosinus phi and cosinus phi and y cosinus phi, y sinus phi can be related to this equation. So it is a little geometry, but not very difficult to understand. And so this equation, I can write it differently. I can write it f of x and y, and here put a function which is equal to 1 on the line and 0 elsewhere. So I have here this equation. And this is the equation that this morning we wrote. And this equation, which is called Radon transform, Radon transform is the forward equation of this computed tomography problem. Okay? Now, what I am going to give you now is that why this equation is called Radon transform, because Radon was a mathematician who were interested to this equation, and he proposed an analytic solution for the problem. That is why this is called Radon transform. So the forward problem here is, if I know f, compute e. No problem. We just has to, again, we have to discretize this equation. I am going to talk about this discretization, and you will see a little later about that. But for now, just I am going to give the analytical solution given by Radon. And Radon found this solution, which is 1 over 2 pi integral over phi 0 of pi integral over r, and then you have here derivative of g with respect to r, and here you have r minus x cosinus phi minus y sinus phi. This is the solution that Radon proposed as the solution of this equation. So you can say that, okay, Radon proposed a solution. Actually, this solution stayed in the books for about 35 years, and nobody was really looked at this equation. And after 30 years or 35 years, when the people started to use this computed tomography, started to try to see, okay, Radon has proposed this solution, trying to use it. Okay? And however, when they tried to use it, they saw that, okay, what do I have to do? What are the different steps that I have to do to arrive to compute the solution? Okay? Let's start by step and to see how, if you are faced to this equation and you want to use it, what are the different operations that you have to do? You are given G, okay? You are given G for different phi and for different R. The first step is you have to compute derivative with respect to R. In mathematics, you can do the derivation. If I given the expression of G, okay, you could do derivative. But numerically, how to do derivative numerically? it is not a very easy problem. Computing the derivative of a function numerically is not a very simple problem. Anyway, for now we are not going to discuss more in detail, but the first step is computing derivative. I am going to write this as operator D, which gives the derivative dg. And then, okay, I have obtained this derivative. I let write it g prime of R and phi. And then you have to compute this integral. But this integral has some difficulty. Let me note this quantity to be equal to R prime. So you have an integral to compute, which is a function divided by R minus R prime, and you are integrating with respect to R. This has some difficulty. Why there are some difficulties? Because R minus R prime may be equal to 0. So there are some difficulty in this. But if you, let me write here integral of f of t over t minus t prime dt. Somebody can tell me what is this? This is the Hilbert transform of f of t. Let me note it f tilde. There may be 1 over p somewhere, but if not, we can just put it here. This is called the Hilbert transform. And if you look at this, it is actually just change the place of R and R prime and note it T and T prime. And so you have a Hilbert transform to do. Okay? So the next step here is to do a Hilbert transform. Okay? So we are here, we compute this here. And finally, we have to integrate with respect to the angle phi. And this operation, this last operation, is called back projection. And I will talk about this a little later. Just for now, we are defining this last operation. Assume that what is the result here is a function of R and phi, and you are integrating with respect to phi, and the results you are obtaining. Okay? So these are the different steps that we have to go from G to F. May not be very familiar, but like the convolution, equation of the convolution that we had, we went in the Fourier domain and the convolution became multiplication. Okay? Here also we are going to the Fourier domain. It is interesting to go in the Fourier domain and try to see what happens in the Fourier domain. Okay? Can you, somebody tell me, derivative of a function in the Fourier domain would be? Let me remember you here. If I have f of t and its Fourier transform f of omega, derivative of f with respect to t, its Fourier transform is g omega. And for the Hilbert transform, also, you have a relation in the Fourier domain. The Fourier domain of f tilde would be equal to f of omega multiplied by sine of omega. So these two properties, we are going to use it here. Derivative, so I am going to note the Fourier transform of G with respect to R. We are working on R for now, okay? So for fixed value of phi, the Fourier transform, one-dimensional Fourier transform with respect to R, I am going to note it G of omega and phi. Okay? Omega is the Fourier transform representing to R. So this operator D in the Fourier domain would be G omega. Okay? I expressly changed the not short omega but great omega in this case, just to mention that this omega is the corresponding Fourier transform of R. Okay? And then you have here a Hilbert transform, which is just sine of omega. And then you have to do inverse Fourier transform. And if you do inverse Fourier transform, then you arrive at something which is the result that is here. I am going to note it J tilde of R and phi. So here, after inverse Fourier transform, I did a Fourier transform. I did a Fourier transform, doing this, inverse Fourier transform, and here I will have J tilde of R and phi. And finally, back projection, and I obtain of x and y. All these operations, which is going from here to here, doing a Fourier transform, doing this and doing this to arrive here, I can summarize it, all this, I can summarize it as an operation of filtering. Okay? What is a filtering? Filtering is go to the Fourier domain, multiply by something, and do inverse Fourier transform. What is that something that I have to do here? I have sine of omega multiplied by omega, and I have here only absolute value of omega. And so this is a filter. Whole of this is a filter. And then we have back projection. I will be back on this back projection a little later. And the whole operation is called filtered back projection. Filtered back projection. So this is the method that is implemented in many scanners actually nowadays. Okay? Not exactly this, because the real scanners, the geometry is not a parallel geometry, is a fan beam geometry. But the main idea is here, how to do these operations. So now let me talk a little about this back projector operator. Do you remember that this morning we talked about adjoint operator? And what is interesting here is that this back projection operator is the adjoint operator of the radon transform. So if let me go here. If I can make a here we had radon transform, okay? I can make a design here. Here we had 1D Fourier transform. Another relation, this was one relation that we could find. And let me talk about this back projector operator. If you remember, let's talk about the Fourier transform a little later. If you remember, we talked that back projection operator gives from here to here with the following properties. That this back projection operator, let me write it first, is integral of g of r and phi phi d phi 0 phi 1 over phi, and this result is something which is, say, I am not going to call it f, I am noting it b of x and y. This is the operator of back projection. And it is interesting to see, we would like that B be equal to F. If it was the case, this operator was invertible, but this is not the case. This back projection operator, which is here, can you understand that R actually, let me rewrite this, because you may not understand why. Here we have integration with respect to phi, and the result depends to x and y. It seems a little strange, no? It is not actually strange, because R is x cosinus phi plus y sinus phi phi. So you can understand now that when integrating with respect to phi, the only things which stays is x and y at the other side. And now what is important to know is that I'm not going to prove it here, is one of the exercises also. We can show using the inverse Fourier transform, inverse radon transform, you can show that B of x and y in fact is equal to f of x and y convoluted with a function which is very nice function, which is this one. This is a two-dimensional convolution, okay? So this relation which is here between back projection and a convolution, you can also write it differently. X power 2 plus y power 2, you can write r power 2. And here in the coordinate, cylindric coordinate, you can write it differently. But let me stop here. And so this relation also give you another scheme to do reconstruction, which is first